Good morning, Dr. Kapani, and good morning, Dr. Ryan. Thank you very much for accepting the invitation today. Nice to see you here. So welcome everyone to episode 7 of Loops. For all those that come across the episode or the initiative for the first time, this is a live webinar series focused on exploring the innovation produced by the Horizon 2020 funded projects. My name is Daniela Bruccoli, and I'm in charge of the communication at Veltha, who is the organizer of this initiative. And I'm very happy to be here today. So today's topic is going to orbit around the innovation in the automotive sector. And our special guests are Dr. Kapani, who is the project coordinator of CarE-Service, and Dr. Ryan, who's the project coordinator of C-Drive. So before moving into the heart of the episode, I would like our guests to introduce themselves. So please, Dr. Kapani, would you like to start with a brief introduction?
Good morning, ladies and gentlemen. Thank you very much for this invitation. I am a researcher at the National Research Council of Italy. In particular, my research area is on manufacturing business models and business models for circularity. But in our organization, we deal in general with advanced manufacturing technologies. At the same time, I'm also the manager of the Lombardy cluster on intelligent manufacturing.
Perfect. Thank you very much. Dr. Ryan?
Thanks, Daniela. Yeah, so my name is Kevin Ryan. I'm a professor in the Department of Chemical Sciences at the University of Limerick, and my research group is in the Bernard Institute. And my research area is in developing silicon anodes for lithium-ion batteries. So we do a lot of research in terms of alloying anodes, and we have a large battery research facility where we look at full cells, half cells, in different cell formats. And as mentioned, I'll be discussing the C-Drive project today.
Okay, great. Thank you very much. Perfect. So now I'm just going to give our audience a short overview of what the episode will be about. So now each of our project coordinators are going to deliver a short presentation of their project and their research. And after that, there's going to be a Q&A session. So I'm going to ask a few questions to our guests, but we also want the audience to ask as many questions as possible. So please feel free to ask them during the live streaming on YouTube or in the chat of the event on LinkedIn. And we'll pick them up at the end of this discussion. So now I'll give the floor to Dr. Kapani, who's going to take us on a journey in CarE-Service project. So please, the floor is yours.
Thank you very much, Daniela. So let me share my screen and my slides for this introduction. Just confirm me that you can properly see my screen. Do you?
Yes, you just need to put the presentation mode on.
Presentation mode. Voila.
Perfect. Thank you.
So I will introduce you the CarE-Service project. It has a long name which depicts the topic of the project, which is Circular Economy Services for Reuse and Remanufacturing of Electric Vehicles through Smart and Movable Modules. I simplified the title, but you can understand that this is a project dealing with circular economy of electric vehicle. Here you find the figures of the project. We are 15 partners in multidisciplinary field. So we have an automotive OEM, which is Fiat Chrysler Automobile, now Stellantis. The project is coordinated by my institute, the National Research Council of Italy. Among the scientific side of the project, we have Linköping University, the CSIC in Spain, as well as the Fraunhofer Institute. Then we have companies in different domains. We have recyclers in the automotive field, recyclers of materials. We have a compliance scheme. We have providers of ICT technology in the circular economy. We have specialists in the battery business, in the consulting around battery business. And we also have a car sharing company, EVI, and the Joint Research Center. Why do I tell you this? Because the project is really, really multidisciplinary. The project was supposed to finish this May, but in fact we got 6 months of extension, so we will close our activity next November. If you find any interest, there is still room for participating. I will tell you how. So what is the point of CarE-Service? The point is the paradigm shift from traditional cars to electric mobility. We all know the projections. We all know that in 2040, more than the 35%, now the estimations changed, will be the share of electric vehicles, but there are problems and opportunities linked to this transition. Here we are picking up some of the points that we address in the project. First of all, electric vehicle, they still have a high total cost of ownership, mainly due to the batteries. And this is a barrier for the diffusion of electromobility. Second, the user's experience, while technology is still evolving, is a little bit limited or critical somehow due to vehicles' autonomy. Maintenance is a little bit engaging, the issue of recharging station. But especially the big point is that in Europe, we do not know how to organize. Now the situation is improving, but in fact, I'm quite rude for the end of life of the enormous volumes of electric vehicles that will reach their end of life in the next years. So in CarE-Service, we are somehow addressing the 3 points. Obviously, the main one is the end of life, but thanks to circular economy, we also can improve users' experience and reduce total cost of ownership of electric vehicles. This is the project philosophy. So let's start digging into the topic. Why this situation? Why we are not prepared to the end-of-life management of electric vehicles? Because they are basically a new product. They are new vehicles. And not all their components, they were designed for reuse, remanufacturing, or recycling. So really, there is a lack of knowledge, there is a lack of consolidated processes and technologies to reuse, recycle, and remanufacture parts of electric vehicles. And also, I already mentioned the design issue is quite relevant. Components are not designed to be reused, or they are not always designed in a structured way to be reused. That's the point. So, in CarE-Service, we have the idea to work on the one hand to new technologies and business models to enable the growth of reuse value chains. And on the other hand, we have the idea to innovate mobility services based on the new reused value chains. The two aspects, they are interconnected into a new ecosystems of mobility products producers and users. About the technologies, what are the main points of our project? We are working at the redesign for circular economy. We are working at the technologies per se, so technologies for disassembly, technology for remanufacturing, technologies for recycling, because in Europe we have a leadership in production technology, so we could, let me say, easily gain the same leadership in circular economy technologies. We are working at the business models to reduce the total cost of ownership of electric vehicles, as well as to enable new reverse logistics chains and new reuse chains. From the service point of view, mobility service point of view, the idea is to push new sharing integrated services thanks to the benefits that can be provided by circular economy. We are also working transversally to the regulatory framework, because we know that regulation is one of the major challenges for circular economy. So our project is also transferring guidelines and opinions to the policymakers as a European project. This is the underlying scheme that we are following in the project, and I would like to drive you through this. So imagine, let's start from vehicles in use. not all the vehicles, but the vehicles of the car-sharing fleets. Okay, so imagine that there are car-sharing companies in Europe and in the world that are managing their vehicles. Their vehicles, they are used by citizens in the frame of some innovative services that I will tell you later on. When these vehicles reach the end of life or when they need to be repaired, they will undergo these processes through innovative disassembly and testing techniques. So valuable parts of these vehicles will be disassembled, and we are working in the project at 3 streams: the technopolymers, the metals, and of course the batteries, which are the most valuable part of electric vehicles. But we decided to concentrate on these 3 streams of products. So after disassembly and testing, if these parts, they can be recovered, reused, or remanufactured for the production of spares or for the production of new vehicles or of new parts for new vehicles or of new segments of remanufactured vehicles, well, they will be rewarded by the recovery chains for that. But we are also planning uses in sectors that are different from automotive, for example, in the furniture sector, in the energy sector, in the chemical sector, and so on and so forth. I need a pointer. Just a second, because I realized I need a point. Okay. So this is the circular economy scheme adapted to electric mobility, considering the car sharing issue. Why the car sharing? Because this is, let me say, a protected environment where it is easier to start with these discussions compared to the business to consumer sector. When we can prove that these concepts work for car sharing businesses, which are a little bit a B2B still type of business, even if they serve consumers, the following step will be to extend this consideration, these approaches to the European manufacturing car industry. Now, let me show you some key hints of the project and some major results that we are developing. First of all, the smart mobile modules. What are the smart mobile modules? They will be trucks, mobile units that will transport the technology which is needed to disassemble and test products from end-of-life cars directly where this is needed, which means at the dismantler's side. So this is the concept of mobile technology that is transported where it can be used, because usually the dismantlers, they have not, on the one hand, the knowledge of the new products. On the other hand, they have not the possibility to invest in, for example, robotics disassembly systems for batteries, especially in this transition period where the volumes of electric vehicles, they are growing, but they are not justifying yet big investment from dismantlers. So in the transition, at least, we need the concept of mobile technology. In particular, we are developing 2 types of modules. One is dedicated to the disassembly of battery packs at dismantler site through robotic system. Another one is dedicated to the on-site testing and certification of what is disassembled, in order that it can be re-put in the market with a guarantee, with a certification. Okay, so this is the concept of mobile technologies. What about batteries? What are we doing for batteries? Which are the most added value part we are working with? We are developing robotics assisted technologies to disassemble batteries from packs to cells. So in the first step, to extract modules from battery packs in the mobile unit I have just told you. In a second step, to disassemble cells from the modules in stationary plants. We are developing new testing technologies that find a compromise between time and sustainability of the testing activities. They are needed to remanufacture new batteries. They are needed to give a guarantee on cells, modules, and packs. We are working also at the recycling side of batteries. When it's not possible to remanufacture and reuse, they need to be recycled. So we are working at mechanical pretreatments and how hydrometallurgical processes to recover the black marks and key metals. And we are also working in the application side. In particular, we have demonstration scenarios in the energy sector, solar panels, automotive, chemical, but also in the medical field. I will tell you something later on. This is on the battery side. What are we doing for the metals? For the metals, we are working at technologies for reforming metals and for disassembly structural parts of metals. Reforming means take a metal sheet which is used and give it a new shape for a new second use, more or less. Okay. So imagine that in the future, it can be technically possible to extract a roof of an old car and, for example, remanufacture a hood for a new car or as a spare, which gives a lot of flexibility. The problem of structural parts, which are the red ones you can see now here, is that at the moment they are soldered, so it is not possible to extract modular parts in order to rebuild new structural parts for new cars. So what we are doing is to develop new desoldering methods and new modular joining techniques in order to modularly reuse these parts to make new components for new cars or fleets or new cars produced by OEMs or spares. For the technopolymers, we are working at the materials recycling level. So the idea is to select some valuable technopolymeric parts of cars and develop new compounds in order to reuse the material that we can extract from that, to be reused in new automotive parts as well as in new polymeric parts for other applications. So we are here talking about separation of metals and non-metal parts, grinding, formulation of new compounds, extrusion, and testing. Another very important part of our project is that we will enable the business of the reuse value chain through an ICT platform. Very important. This ICT platform will build a sort of orchestrated place where all the actors of the reuse chain, they can cooperate, but will also serve as a marketplace for the professional exchange of reusable parts. Reusable means remanufactured, recycled, and so on. So the platform is a trusted environment where you can find tested and certified parts. You can put your needs, and then the supply chain activates based on the available volumes of cars and intermediate parts to provide what it's needed. So in a certain sense, it's market put. Another important thing is that the platform is linked with the mobile modules, because the parts that are certified locally by the mobile module will be made available immediately inside the ICT platform, and also the disassembly operation will be visible in the platform. The users, they can book the services of the module as a service of the platform per se. Finally, about mobility services, we are designing with our partner in car sharing services which are performance oriented, which are a little bit innovative in car sharing. For example, we are thinking about car sharing in rural areas, integration of urban and non-urban car sharing, integration of usage among companies and citizens, this type of things. Okay, I don't know how much time is remaining, but if I still have just a few minutes, I can, of course, I can tell you that we are, and we have a stakeholders group, a consumers committee in which you are invited. Just visit our website, you can register, and you will be invited to all of our events. But we are also looking here now for replicators and potential users of our solutions. So if you want to come in contact with us, just visit our website. What are the results? Okay, the mobility services, they are already designed, they are being tested in practice, and so we have tests with companies and citizens for the new mobility services. We will run a European survey also to assess their potential, so if you are interested, you can tell your view. Few words about the mobile disassembly system for battery packs. This is what will be included inside the track: a robot for the disassembly of modules from battery packs in a cooperative environment, very efficient, and especially in a safe environment. For the disassembly of battery cells from modules, we are developing collaborative solutions. You see man-machine interaction, because here the operations, they are in a smaller scale, and still the goal here is to guarantee safety, ergonomy, as well as efficiency of this operation. The reuse applications we are working at, they are in the energy sector, so we are applying reused cells and modules into stationary application lighting systems, for examples, and renewable stationary solutions in solar panels. But we are also equipping remanufactured batteries into mechanical ventilators. This is obviously one application that we developed to address the COVID issues with some medical companies. We are also developing a concept in general of modular batteries, something like that, okay, for example, for portable applications. For the mechanical pretreatment, as I told you, we are extracting black mass and inorganic pigments after not only for mechanical pretreatment, but in general for recycling. So we're mixing mechanical pretreatments and hydrometallurgy. For the regulations, we have already provided very precise guidelines and suggestions for the new regulation to the European Commission. This is a public deliverable you can download if you're interested into our website, as well as for the other public deliverables. So please take a look. For the technical parts, we are working in a scenario where you see, cut the roof of a car, and we realize parts such as disc cover brakes for new vehicles or as spares parts through reforming techniques. This is just some image of the new laser desoldering techniques that we are developing to dismantle structural parts of vehicles in order to build new structural parts. For new cars, we are also working, of course, at the business models here, because imagine, just as an example, if you can reform new metal parts, then you can also offer concepts such as a design upgrade of our old vehicles. So OEMs, or maybe it can be offered to car sharing fleets, they can have an upgrade of their vehicles, both in the aesthetics through new remanufactured parts, as well as in the functionalities if we want to provide new remanufactured electronics or mechatronics and something like that. These are the business models that are called remanufacturing with upgrades. And from the material side, we have our partner have developed new materials formulation, which proved to be very, very effective compared to new materials. They are implemented already in products. And the platform is already working, let's say, in the prototypal phase for the different users. So for the dismantlers, for the remanufacturers, for the providers. The three streams which I introduced, they are reflected, of course, in different sections of the platform. So the users, they can book the service of the modules, they can buy parts when they need, they can also post needs of parts in order to trigger the behavior of the different value chains. These are just some images. Let me close just with this. We are in the final phase of the project, so we have organized a calendar of a number of events from now until November. They are both training events on all the aspects which I told you, so events that are meant to present and tell information about the state of the art of these concepts, of these technologies, and so on. So very interesting also from a cultural point of view. But especially they are also demonstration events where we demonstrate in practice the behavior of all the results applied to new scenarios. Of course, basically they are all virtual, but we are also studying the possibility to organize some physical event if it will be possible, especially after summer. So you are very warmly invited to visit our website to take a look at the calendar of events that we have put there and to register. They are, of course, all for free, all virtual. So we're really looking forward to meeting you in our final phase of the project. Thank you very much, and sorry if I was a little bit longer than the foreseen time.
No worries at all. Thank you very much. That was a very detailed and interesting presentation. So please, for any question is welcome, and we'll pick them up shortly. Now, of course, I'm going to give the floor to Dr. Ryan, who's going to introduce us to the C-Drive project. So please, you can hand over. Oh, your microphone. Your microphone is off.
Yeah. So I need to just share here.
Yes. Can you see the button to share? Oh yeah, here it is.
So can you see my presentation?
Yeah, yes, you just need to switch to the presentation mode.
Okay, are you seeing speaker notes, or are you seeing the actual presentation?
Just view and presentation modes.
Are you seeing the presentation mode, or is it because
now it's just a PowerPoint and with the list of the slides, so there should be
a second. I'll start again. So
from begin.
Okay, so you see just the presentation. Is that correct?
Yes.
Okay, so first of all, Daniela, thanks for the opportunity to present today. So I have a short presentation that's going to overview the CarE-Drive project. So the title of the project is Silicon Alloying Anodes for High Energy Density Batteries comprising lithium-rich cathodes and safe ionic liquid-based electrolytes for enhanced high voltage performance. So there's quite a lot of detail in the title, but it very much explains what we're doing. So it's very much about changing the chemistry of lithium-ion batteries to improve their performance. So I'll speak a little bit about the consortium in more detail in a minute. So just a little
Dr. Kevin, sorry to interrupt you. I'm very sorry. Maybe if you go to view on the top of the PowerPoint, we can have a bigger size of the reading view.
So you should be seeing the
because it's a little bit smaller.
Yeah, but I am in slideshow mode, so you're not seeing just the presentation screen then, are you?
No, no, because we see the whole PowerPoint. You should. I mean, if it doesn't work, then you can just move on.
I know that it's. I'll just stop sharing for a second, and then we'll share. Hopefully, we can get this right.
Yeah, no worries. Okay. Yeah, it's still.
Yeah. Okay. So it's.
Yeah. If there's no other way, then it's fine.
Maybe I can just increase the. So.
Oh.
Is that better?
Yeah, it's better. Yeah, definitely.
Okay, so
Perfect. You can move on. I'm sorry.
okay, so I'll just have to flick through them in this few months. So yeah, so I've gone through the title. As I said, I'll go through the consortium in detail, just a little bit on University of Limerick. So we're a university in the west of Ireland. We have about 16,500 students and over 2,000 students at postgraduate level. And we're based on the banks of the River Shannon. So I'm based here on the bottom image here on the left, which is the Bernal Institute, and the Bernal Institute has 4 key areas. So they're molecular nanomaterials, pharmaceutical materials, biomaterials, and composite materials. And then within the molecular nanomaterials, this is where I lead that particular cluster. And then within that, we have the battery team, which is myself, Dr. Hugh Geeney, Dr. Ty Kennedy, and Dr. Shalini Singh. And between us, then we have a research group of about 30 people where we have expertise in silicon anodes, full cell batteries, alternative ion batteries such as sodium, potassium, aluminium, solid state batteries, and we've also a number of industry projects, for example, sensors for state of health monitoring. So if we just go to the key project goals of SciDrive. So SciDrive is about making the next generation of lithium ions, so improving the performance. So we're looking to enable new materials breakthroughs by delivering 100% active silicon anode, a solid polymer ionic liquid-based electrolyte, and a high-capacity lithium-rich cobalt-free cathode. And I'll explain in a little bit more detail why this particular composition, we started to look at. We also have a full theoretical modeling work package, so that allows us to look at the interfacial processes. And then within this particular call, we're not just designing the materials components for the electric vehicle use, but also the second use application. So you're ensuring that you have battery chemistry that can go for not only 1,000 cycles, which would be the typical first life, but also up to 5,000 cycles. So the second use application is very, very important. And then we also have the material recycling then, which will come in beyond the second use application. So in terms of the chemistry that we have, it will have a much higher energy density, a longer cycle life, and allow for faster charging, which is addressing some of the critical challenges with EVs. It also has improved safety. So by moving to ionic liquids, which have a much lower flash point than, let's say, the organic solvent-based electrolytes, then we have a much safer battery. And obviously, the material recycling then includes, I suppose, not only in terms of at the end of use and breaking up those materials, but also elements where we take cathodes and anodes and repurpose them in batteries, so regeneration of those materials. I think it's always useful to talk about the I suppose a real world example, and unfortunately I have a lot of animation on the slides, so this is not going to work in this format, so I'll try and make this work. But so I suppose here in Ireland, like for example, if you take the Kona electric vehicle, and it's a good one to pick because the Kona has exactly the same model in both the electric vehicle and the internal combustion engine. So you're essentially comparing the price based, but they just have a different drivetrain. And if you were to take the cost of the Kona outside of the subsidies, it would be double the price of the petrol-based vehicle. And then your range is 450 kilometers, probably 400 kilometers in real-world use versus the 800 kilometers for the petrol electric vehicle. So there's a lot of movement required in terms of bringing down the cost of EVs and increasing their range. And the only difference between these two vehicles essentially is the price of the battery. So if you look here on the right hand side, we have I suppose, what are the key components of your battery. So these are your anodes, your anode and cathode, and we also have the electrolyte. Now, if we take the current material that's used as the anode material, that's graphite, that has a capacity of about 350 milliamp hour per gram. And we can get a rapid or a significant jump in capacity by moving from graphite to silicon, because silicon, if you see in the bottom right here, is of 4,500, or sorry, over 4,200 milliamp hour per gram. And you also see that silicon has a relatively low voltage versus lithium plus, so it is a very good material for the anode. But the challenge with silicon is that the process that silicon uptakes lithium is different to graphite. So where with graphite, you essentially have sheets of graphite or sheets of carbon sheets, your hexagonal sheets, and your lithium intercalates between those sheets. Whereas with silicon, it's an alloying process, and what happens is that you get 4.4 lithiums for every silicon atom once you cycle with lithium, and you get so versus a 10% volume increase with graphite, we get a 300% volume increase with silicon. Now, if you were just to do this with a bulk piece of silicon similar to what we would take for the size of a graphite flake, it would shatter. And this is the image that I'm showing here, which is one of these overlaid images. So we actually have to develop silicon in a different form so that it is stable. And we do this by using silicon in a nano form. So if I move on to the consortium and chemistry, and again, I apologize because this should be in presentation mode, but it's not working. So I might just try and move around some of these images so that we can actually see them. So this is our consortium. So it's led by the University of Limerick. We have 16 partners in total. We have partners both in industry and academia and across a number of countries in Europe. The project is from TRL 3 to TRL 5. So we're developing new chemistries, but taking that right through to new cell design and prototype demonstration. So if I go through some of the partners, so I'll just bring this to the front for a second. Hopefully this will work. So we're spread into 7 work packages, and here on the bottom we have the work package leaders. So we have specific work packages on the anode development, the electrolyte development, and the cathode development. In pillar 2, which is the battery validation and modeling, we have full cell testing and component modeling, and this is by CEDATEC and DLR. And in pillar 3, we have the prototyping and feasibility analysis, and this is prototype testing and validation, which is done by the FAM Research Centre, where formerly LitHups. And then the end of life is led by Leuven, and then there's the other partners form part of each of these work packages. And we see that the modeling input and the LCA recycling analysis comes through in all the work packages. So if I probably just easily bring this one to the front now. So this kind of is a schematic just showing all of these chemistries together. So we've KIT are developing the high voltage lithium rich cathodes, and this has been scaled up by ZSW. We have partners in Italy, both ENEA and Politecnico di Torino, which are working in the area of the ionic liquid electrolytes. And there's 2 stages in this. The first is use of ionic liquid electrolyte, and then the second stage is a polymerized ionic liquid electrolyte, which is solid state, which will lead to an even more stable battery or a more safer battery configuration. And then at the anode side, then we have silicon coated 3D nanowire anodes, and I did want to show what this looks like. So I'll just bring this to the forward. I know this is a little bit awkward, but so this is, I suppose, just to give a context to the chemistry involved. So at UL, we have developed a process to grow copper silicide nanowires directly from a copper substrate. So the copper, this is essentially the electrode, and we can control the density and orientation of these nanowires. And then with our industry partner who are in the Netherlands, who are Smith Thermal Solutions, so they have an expanding, it's basically a plasma enhanced CVD process, which can deposit silicon So the silicon then deposits onto these nanowires. Now, if you just deposit the silicon, for example, onto the bare copper, we get the cracking similar to what I showed in the previous slide. But when we deposit it onto the nanostructures, it radially coats the nanostructures. And because we can control the amount of silicon that's deposited onto these copper silicide nanostructures, then we can get a high area loading. But more importantly, because these copper silicide nanowires don't cycle lithium themselves, they act as conductive pathways. So what we get is because of this, then we're addressing the poor conductivity of silicon. And because then these are nanostructures and related to their surface area, we get very, very stable cycling. So we can get, we've shown over 1,000 cycles with these material. Whereas if you took a bulk piece of silicon, you would only get, for example, only a handful of cycles or even one or two because the material shatters. So if we're to, I suppose, look at the advantages of the combination of these approaches. So if you look at the cathode side, it's what KIT are developing is a cobalt-free layered oxide, and it's lithium rich. Now the advantage of being lithium rich is that compensates for starting with the silicon material. So we don't have specifically to deal with the pre-lithiation as a major issue in other silicon coatings. Or silicon-based anodes. And what we're doing here with silicon is we're doing 100% silicon, whereas if you take silicon in batteries at the moment, at most you will get is 5%. So by doing 100% silicon and directly grown from the electrodes, we're eliminating a lot of the binders and the conductive additives. And then I suppose on the cathode side, because it's cobalt-free, there's a lot of issues, ethical issues in terms of use of cobalt, because there's child labor used in the mining practices in the Congo. So there is being able to achieve a high performance battery that's cobalt free is a hugely important. And the part of the modeling and the experimental aspects is to optimize these electrodes in terms of with coatings, and I'll speak a little bit about the results on that with dopants and coatings to improve performance, such as the SEI issues, etc. We also have aqueous processing, so that addresses the environmental issue. So each of our components are designed from the start to make them more suitable for recycling. So we're building that right into the start of the battery configuration. The ionic liquid electrolyte is a lot safer than the organic electrolyte. So in the event of a crash where you're going to get a piercing of your battery cells, the thermal runaway is a lot lower, or the flash point for thermal runaway is significantly, it's higher than it is for the organic solvent. So it's a much safer chemistry for use in electric vehicles. And then, as I said, with the silicon nanowire coated 3D electrode, we're eliminating the binder and conductive additives, but we're also eliminating graphite. And there is major issues with graphite in terms of supply chain in Europe. So just continuing on in terms of a major factor, and again, this is back to the cost of electric vehicles, is to reduce cost. So if you look at the left here pie chart, this is the state of the art, which is about €255 per kilowatt hour. And then the components then are your anodes, which is 24%, your cathode 28%, other costs 35%, etc. So we've outlined SiDrive in 2 generations, which is generation 1, to bring that cost down to under €65 per kilowatt hour, and then generation 2, which is the NMPB30 target, which is to bring it down to €75 per kilowatt hour. And you can see that there is the overall pie is reducing, which is what we want, but then you can see that there is changes in, so the anode does cost more because we're using silicon, 100% silicon, but then we are reducing other costs because we don't have binders and conductive additives. The cathode is reduced in cost because of the elimination of cobalt, and the electrolyte goes up in cost, relative cost, because of the ionic liquids. But in terms of the total chemistry, we have outlined pathways to achieve this target. So I suppose in terms of the project, so we're halfway through the project, and we're very much on target in terms of the milestones and deliverables, despite the fact that COVID-19 and the shutdowns occurred essentially 1 year into the project and shut down a lot of the labs. So it was a fantastic achievement by all the groups, all the participant groups in the consortium, to be able to deliver on the project goals. So I suppose I'm just going to share with you just a couple of works that we published from the work. So this is and this gives you a better sense of the chemistry involved. So this is a nanoletters paper that essentially is a joint paper between ourselves and Smith Thermal. So if you look on the left hand side, we see the process for growing of our copper silicon nanostructures. We use a wet chemical process. We send these substrates then to Smith Thermal, who do the plasma enhanced CVD. And if you look in the middle image here, you can see an SEM image of the nanowires in A. In B, we can see this in more higher resolution, and C and D. So you can see that these are A is the nanowires before coating, and then C and D are A and B are before coating, and C and D are after coating. So you can see that we have narrow nanowires, and then after coating, we're getting this a substantial thickening of the wires. And if you look at the inset in D, you can actually see, and this is further shown in E, we can see that the copper silicide nanowire, which is the brighter white line inside the amorphous silicon nanostructure. So we have a very, very high loading of amorphous silicon, and we have a very excellent conductive pathway. And within the consortium, so this is just showing one aspect. Once we have these substrates, then these are sent to Siditech, who are do the full cell chemistries, and they also take the cathodes from KIT and then bring those together in full cell chemistries. But in terms of with these nanowire anodes, we get a very, very excellent rate capability, and then we get a very, very high specific capacity, and we get a further improvements on this in terms of by controlling different properties such as the coatings on the silicon nanowires for artificial SCI, etc. And just one other piece of work that just to I suppose show an example from the SciDrive project. This is a work that came out of ourselves, UL, KIT, which are on the cathode side, and the ionic liquids from ENEA. And essentially here what we were looking at is so that they're developing ionic liquids that would that can be used in lithium-ion batteries. What we're studying here is how do the ionic liquids work with silicon. And this is the first time that this had been studied. And what we found was that if you add a small amount of additives, which such as ethylene carbonate or vinylene carbonate, to the ionic liquids, this provides. So we're only talking about 5% here, but this provides enough of material to allow for a degradation to form a stable SCI. And then with for example, the vinylene carbonate and the ethylene carbonate, these perform a very flexible SEI layer on your silicon nanowire anodes, which allows you to get to very stable cycling. So if you look at B here, I don't need to go through all these in too much detail. If you look in B here, we're comparing the no additive situation, where we can see that there is very, very poor performance. And then when we have the 5% VC, we get a stable SCI layer, so we get a much more stable capacity retention. And then we can see the performance at different C rates. So we can see that, for example, that as we go through C, 2C, 5C, and then back to C over 10, you get a lower capacity, which you'd expect, but you recover that capacity when you go to higher C rates. And in actual fact, if you compare this to graphite-based materials, they would not be able to perform at a similar level. So you would not be getting any capacity at a very, very fast charge and discharge, and you wouldn't regain that capacity when you return to the lower charge discharge rates. So in terms of timelines, just to give an overview of where SciDrive is. So TRL 1 and 2 were already done before the start of the project. So really the project is about taking these chemistries and bringing them all together and making them work in a full cell chemistry. And so we have scaling up the anode materials, scaling up our nanowire growth process, our morphosilicon deposition. So we're now up to 10 centimeter squared scale for those electrodes. And we have large scaling of the cathode material, and we have full cell battery chemistries demonstrated by Cytotec. The project will run from TRL3 to TRL5, and then with a pathway then to the greater than 450 watt-hour per kg by 2030. So within the next 2 years, this is the target that we're pushing towards, which will be 350 to 400 watt-hour per kg. So that brings me to the end. So, and I'd like to thank you very much for listening.
Thank you very much, Dr. Kevin, for this insightful presentation of the project itself. So yeah, I have a couple of questions, but I was also actually wondering, since the two projects focus on different aspects of, in a way, the same sector. So one focuses on the design of new batteries, new batteries, and the other one focuses on the reuse and remanufacturing of previous components. I was wondering, do you have any curiosity or any questions you would like to ask each other about the two projects?
Okay, I suppose maybe let me start, because I must say I found your presentation very interesting. I suppose something we're considering now, I suppose, in terms of the recycling aspect is the possibility of reuse, like rather than, let's say, breaking up your batteries and grinding them up, reusing, let's say, for example, the cathodes, regenerating that cathode. Now, we probably can do this at an experimental level. You know, I mean, we can take apart a battery, take out a cathode, and then, you know, regenerate that material. But what do you think about the possibility of doing that at scale, for example, let's say, if you're in terms of commercially?
Yeah, no, I think it's definitely an interesting argument which should be and could be investigated, because in fact here the point is the scale of these operations, and we are also considering a lot this issue. For example, the fact of using collaborative robotics can be something good for certain scales, but then we are also imagining some more intensive automation when the volumes will grow. So for sure it can be done. We should understand a little bit more from the batteries you are designing, and then see if we can exchange any idea or concept like that based on the type of technologies for, let me say, disassembly, reusing, and testing that we are developing. So to see, first of all, if they fit with your parts, with your battery concept, and then I would find it very, very interesting. In fact, this was also my question to you, because you are imagining a new concept of batteries also at chemical level. So are you also at the same time imagining how to reuse, to recycle these batteries at their end of life, and what is the state of play of this issue eventually in your project?
Okay, yeah, so we do have LCA and recycling form a work package within our consortium. So I suppose because we're developing a new chemistry, so we're able to look at it from a holistic viewpoint. So they're actually involved at an early stages. When we are suggesting, let's say, a new material, there is elements to be considered then of how that will, in terms of the recycling aspect, and it actually throws up some interesting conundrums. So, for example, if you take cobalt out of the battery, that's fantastic from an ethical viewpoint and from a cost viewpoint, but you actually make it less interesting from a recycling viewpoint, because there's no cobalt to be recycled. So that's why the reuse is forming a greater part of our priority, because if you can actually take that lithium-rich cathode and regenerate it and reuse it, then you're not putting any, or you're much lessening the requirements on. I suppose there's no value in grinding it up, but there's certainly a huge amount of value in reusing it.
Yeah. Very interesting. I think we can continue afterwards.
Absolutely, yeah.
Daniela, you're muted.
Sorry. Yeah, sorry. I was just saying I'm glad there is room for future collaboration. And I have a question actually, because both projects are in a sort of way focusing on designing, but also creating new batteries out of previous ones. So my question is, how much out of these batteries can actually be recycled?
Can be, you mean recycled or reused?
Reused for
in general.
Yes.
I would say the 100%, they have to be reused, exploiting the most promising strategy among pure reuse, remanufacturing, and recycling. So all of them, they have to be reprocessed at the end of life.
Okay.
There is a big uncertainty, for example, for what we are doing, because the uncertainty is on the percentage of batteries that can be, for example, remanufactured. It means that they still have to preserve some functionality allowing the remanufacturing, because there are certain batteries that should immediately go to recycling. They have several damages for a matter of security and so on. So we are trying to estimate percentages in industrial and business scenarios in order to understand what is a potential flow of batteries that can be recovered through reuse or remanufacturing or recycling. We are still in the middle of these estimations, but at the end, we are preparing many simulations.
Okay, thank you very much. And what about the side drive project? Because in the design of these new batteries, you're also taking into account the recyclability and the environmental aspect of it.
Yeah, I would agree. I don't see any reason why we can't have 100% reuse. I think the second use certainly is where there's a huge, I suppose, a huge advantage there in terms of how you can, I suppose, look at in terms of energy generation and renewable energy and the requirement for stationary storage, and then you suddenly what we're going to have in the next 5 to 10 years is a huge amount of electric vehicles coming to end of life, inverted commas. Maybe they're 10 years old, but then even at 60% or 70% of their original capacity, they're still going to be a very valuable commodity for stationary storage. I think the challenge there is that this is where the ability to monitor or to understand at cell level or module level the state of health of those batteries. So so that when you are repurposing them, then that they can be used safely. So particularly if you're going to do it on a large scale stationary storage where you're putting a lot of these battery packs in series, you do need to have very, very accurate way of monitoring the cell health.
Do you have an estimation of the yearly number of batteries that will reach the end of life in Europe in the upcoming years? This is more a question for.
Yeah, I suppose I don't have that answer, but I suppose we're still only talking like at a very low percentage of cars that are EVs, but and even so it's really only, but this is even if you only look at Ireland, the number of electric vehicles that were purchased this year is up, I think, 600% or 700% on previous years. Now, obviously, that's from a small number, but we are going to reach a point where we're going to have an equal number or greater number of electric vehicles than internal combustion engines. So it's going to be an exponential rise, and you are going to have in the next number of years, we are going to start to see end of life, and this is going to be more and more of an issue.
Okay, perfect. So we ran out of time, unfortunately, and we don't have questions from the participants. So I'm going to wrap up the episode. But before that, I really want to thank you both for accepting the invitation today and for talking about your projects. They are very interesting. And I hope to getting in touch with you in the future. And thank you again for being here today.
Thanks for the invitation.
Thank you very much for this opportunity.
Oh, thank you. Have a nice day.
Yep.
Bye-bye.
Bye-bye.